All right, so we will go ahead and get started. I am happy to introduce Dr. Pat Burchat, who is going to be speaking with us about both physics and engineering physics, and we will have one more professor who will be joining us momentarily. Pat.
Okay, great. So I'm going to start with an introduction of myself, and then I'm going to ask a few questions about you, okay, so I can learn a little bit about kind of some of the courses that you're taking now. So as you heard, my name is Pat Burchat. People often ask, how do you pronounce my last name? So it's like a little burr and a cat, okay, so Burchat. And I serve as chair of physics advising, so advising in the physics department, and I'm co-director of engineering physics, and I'm an instructor in Physics 61. Actually, I have autumn 2020 there, also in 2021 and 2022, and hi, Mark, great, good timing. And a little bit of personally about me. So I grew up in Canada, and I often say I grew up in a very large family in a very small town. Okay, at about 1,200 people, it still has about 1,200 people in it. And my 8 siblings and I were all first-gen high school graduates. Our parents didn't graduate from high school. And so it shows that education is really powerful, okay, that you can go from parents with no high school graduation to ending up a professor at the physics department at Stanford. And my research, for most of my research career, I did accelerator-based particle physics. So that's a picture of the 2-mile-long accelerator at SLAC, the thing on the left. And I came here actually to Stanford for graduate school to do experimental particle physics. And I did that for about 25 years or so. And then I kind of had the option. At that point, I would have to go to CERN, which is the big complex in Europe, to continue particle physics. And particle physics was a really mature field at that point. And I wanted to be like a student again, get back on the learning curve. And so I actually switched fields to observational cosmology. And it might seem like, wow, that is kind of different. Going from particle physics, understanding the things at the smallest scale, to the universe on the largest scale. But in both cases, we use detectors that have billions of channels of readout, statistical techniques, and the questions are the same. What is the universe made of, and how does all that stuff interact, okay? So now I'm working on a telescope project. The telescope is actually under construction right where I am standing in that picture on the right. That's in Chile, a mountaintop in Chile, about 9,000 feet up. And right now there is about a few $100 million telescope there, completing construction. We're about to start commissioning it and then taking data. So that is enough about me. Oh, one other thing. My undergraduate degree was in engineering science at University of Toronto, which is like engineering physics. And when I came to Stanford, there was no engineering physics program. And I would be advising students, and some of them like, well, I don't know if I want to do physics or engineering. And those were pretty different, okay? And I thought, we need an engineering physics program. So a number of us got together in the School of Engineering and Physics and came up with the engineering physics program about 15 years ago or so. And Mark Capelli is my co-director. And so do you want to go ahead and introduce yourself? And we've got these animations going here, so.
Okay. Oh, good. You could hear me. Thanks, Pat. I didn't plan on saying much about myself, but I came here about 35 years ago, also from the University of Toronto. So I'm also Canadian, lots of Canadians. In fact, Jim Plummer was a Canadian from the University of Toronto, former dean here at Stanford. I think electrical engineering, University of Toronto, Plummer, I think. So I grew up in a small town in southern Ontario, and parents were immigrants from Italy. All my cousins worked on farms. I worked on farms. I didn't have a plan to go to college. And when I was in high school, I was in a vocational high school. One of my teachers said, Mark, have you ever thought about going to university? And I said, not really. And he said, well, you should. And so I switched high schools to a high school that was more, that was better in preparing you for university. Went to McGill University. Didn't intend to study physics originally, but I thought physics was hard, so I guess I should try it. And was admitted to the physics department at the University of Toronto for graduate studies, but I chose aerospace engineering instead, and did a PhD in a fusion-related subject. Why aerospace engineering and fusion? Well, if we ever want to explore the the outer planets and planets beyond our solar system, you're going to need fusion energy to do that properly. And so that was my history. I show a photograph here. Down to my left is the National Ignition Facility. It's a fusion experiment to demonstrate inertial confinement fusion. And an engineering physics graduate, Chris Young, is responsible for setting a record in August. Broke the Lawson criteria for fusion. And that's a great thing. And in fact, his advisor was also a student of mine in mechanical engineering at the National Ignition Facility, Nathan Mizan. He went through undergraduate ME, I'll tell you more about that later, mechanical engineering, and then stayed on for his PhD in mechanical engineering as well. Up to the top left of my photograph is a plasma source. It's called the Z-pinch. It's a source that we actually run here. Unlike experiments that we do at the National Ignition Facility, a few of my students are involved in the experiments, designing the experiments that we carry out there and on the big laser facility in Omega. We also have a machine for learning how to study very dense plasmas, also fusion related. And that's all about me. And now, should we just continue? Should I?
Yeah, so now you're going to go with the
Okay. Whoops. So so today Pat and I are going to share this. I'm going to say a little bit about engineering physics. She's the co-director as well, but then she's going to carry on afterwards and talk about physics more specifically. What is engineering physics? Engineering physics brings together three disciplinary areas, as shown here: math, physics, and engineering. And you might say, well, doesn't engineering also use math and physics? That's true, but you get a little bit more math and a little bit more physics in engineering physics, and then you specialize in an area of interest in engineering that you're particularly interested in. It prepares you to, as we say here, tackle problems that are at the forefront. Multidisciplinary problems that are at the forefront of technology, all right, that in engineering we might not yet be working on. All right? So that's where you go with engineering physics. In engineering physics, you could specialize in several areas of focus. This is now once you get into the upper division where you've already done the core studies that you're required to do in physics and mathematics, and then you specialize in many areas. And one of those areas is renewable energy. And there we ask questions like, how can we use the combination of physics, engineering, to solve or at least address some of the big problems that we have in renewable energy, for example. Right? That's a hot topic right now. It's a popular one for many of our engineering physics students. Another area of interest is, and this is the kind of coupled in some ways, is the specialty we call material science and engineering. And it asks the questions on how you could design new materials that advance the performance of some of the technologies that you might find in the renewable energy specialty. All right, things like, and this is a hot area now too, right? Battery technology. If we really want to get to a point where we can reliably use high efficiency storage methods like batteries, we need new materials. The materials that we use now, lithium ion batteries, nickel cadmium batteries, they're just not going to cut it. They're not going to work to the level that we expect them to work if we want to be able to displace other technologies like internal combustion engines for transportation, for example. Another area that students specialize in when they study engineering physics is electromechanical systems. And many of the courses related to this are in my department, mechanical engineering. There you ask questions like, how can you combine physics, math, and engineering to design the next generation of smart products? These are products that exploit things like mechanical systems, dynamic systems, robotics, and all of that needs to be managed by electric circuits, right? Processors, microprocessors, and computers. Aerospace physics is a relatively new one. I think it's only about 4 years old now in our specialty list. Another popular one for some of our undergraduate students, all right? How can we better the understanding of this space environment and the physics associated with it to design new space vehicles and control space vehicles in a way that gets us places and carries out certain tasks in space. All right? Eventually, for example, we're going to run out of certain resources on Earth, or it's going to become too expensive to mine those resources. Examples like we're going to have to develop technologies to get us to other places, other planets, or the moon, or even to asteroids, and mine resources that are going to help us make those batteries, the new materials that are going to be needed for the new batteries. Right? So that's a popular one, growing in popularity. And then there's one that we call computational science, another relatively new one that might be about 8 years old. And we ask questions like, how can we combine the computational theory and algorithms, many of which, for example, we use in gaming now, but they're very powerful algorithms to solve big problems in science and also to manage big data. Right? So that's a popular specialty. And finally, one that we introduced a few years ago, quantum science specialty. And that one, of course, quantum systems are now, they're not just things that you read about in textbook anymore, right? You could imagine engineers beginning to build computers out of systems that operate at the quantum scale, all right, the quantum scales. Cryptography, as you know, exploits quantum entanglement, and all of these might be something that you see in a physics class now, but eventually in the next decade or so, you're going to see more and more of that cross over to the engineering side. So those are the disciplinary areas of engineering physics. And I think I'm going to now turn it over to you, Pat, right, to talk about. Yep. Yeah, you got this.
Okay, and there was one in the corner of the previous slide. Let me just.
Oh, did I miss
Yeah,
something?
but that's okay. Yeah, biophysics, but
the
there's nothing
biophysics
about
is
it
on the
because it'll show up in physics, okay? And so I'll pick that up then. So how do we contrast engineering physics with physics? So physics really emphasizes, and this is actually an essential part of engineering physics too, that physics emphasizes a first principles understanding of the universe. What do we mean by that? In physics, we try to come up with mathematically consistent, predictive theories, okay, theory that you can make a prediction from, that describes the universe on all scales, from the tiniest to the largest. And in addition, we want to understand the universe by doing observations and experimentation to test the predictions and hopefully and often discover new physics. Okay, so that's actually the most exciting part, is not just verify what we predicted, but perhaps find something new. And then through something like engineering physics, we can apply it to come up with new discoveries. So we have in physics what we call pathways. So in engineering physics, they're called specialties. In physics, they're called pathways. In both cases, we have 7 of them, it turned out. This happened to be. And the first one that I feature here is biophysics. So biophysics answers the question, how can we use techniques developed in physics to advance our understanding of biological systems? So for example, this little movie here, which I think will play, shows some real-time imaging of a brain in a mouse. And you see those little flashes of light there? So basically, they're imaging all these little flashes. In the end, they will be able to stack all the flashes up and get a really high-resolution picture of this brain, okay? And all the techniques that are being used there to make these things flash, what is it, the imaging and stuff, relies on a lot of physics. And so it's using physics techniques to understand biological systems. The bottom one is a retinal prosthesis, so artificial retina, that is being developed to replace damaged retina cells Okay, and so obviously there's a lot of physics in there. The person who does that, Daniel Palenkar, is his background was all in laser physics and fundamental atomic physics. And then he was also very interested in medical applications. And at one point, he actually had a bit of an eye injury in a laboratory and ended up in the emergency room at Stanford University and ended up talking to the head of the new chair of ophthalmology there. And that's how he started this program, okay? So he has now this world-class program in that area. Then another specialty or pathway is astrophysics. So in astrophysics, we'll ask questions like, how are stars born? How do they evolve in time? And also a lot of studies of black holes. Can we detect and study black holes? So one of the ways a star or set of stars might die. And so on the left image for the astrophysics part there, that is an image of gravitational waves, just a kind of artist rendition, going through space. And this is what was detected by that detector called LIGO from merging black holes. And then the one on the right, you may recognize this was an image of radiation around a black hole, and this was done within the last year. So we're actually finding out a lot about black holes now. Other questions could be, how do galaxies form and evolve? What is dark matter? We don't know. We know it's there. We don't know what it is. What is dark energy? We know it's there. We don't know what it is. What is the origin of the universe? And how is the universe itself evolving? So those questions are cosmology. And that's the kind of thing I'm working on now. Another pathway is computational physics and data science. So this picture on the left is a picture of a textbook. The authors, I know all the authors, they're all astrophysicists and cosmologists, okay, but it's called Statistics, Data Mining, and Machine Learning in Astronomy, a practical Python guide for the analysis of survey data. It's a fantastic textbook. It's actually online, and they are always updating it. There are Python notebooks and everything to go with it. So we use a lot of computational techniques in physics. And the thing on the right, you might say, that looks like black holes again. So that is a simulation of merging black holes. So that's an example of what computational physics would be applied to. And then geophysics. Understanding the Earth at all levels is basically physics, okay? I mean, there's chemistry as well, but a lot of physics. And so these are just two images that I found that I thought were kind of representative. The one on the right represents the magnetic fields of the Earth, okay, between the times when the fields will flip. I don't know if you know this, but every roughly, I think, 10,000 years or so, the North and South Pole flip. Okay, so there, with physics, you can actually, kind of calculate what might happen during that time, and will we be able to keep up with that change the way the birds and the bees do? Okay, because they use magnetic fields a lot. The thing on the left is weather patterns and circulations and stuff. And actually, for anyone here who's in Physics 61, we were mentioning the Coriolis force, and I was saying it produces these things called Hadley cells in the atmosphere and everything. That's all physics, okay? Understanding those circulation patterns. So a lot of physics and geophysics. Number 5 of 7, mathematical physics. So this is related to theoretical physics, but theoretical physics is like, how do you discover new theories in physics? Mathematical physics is, what are the mathematical foundations of theoretical physics? And how does math inform physics, and physics inform math? Okay, sometimes physicists are winning math prizes because they end up being able to make big leaps in mathematics using kind of physical reasoning. So if you like both math and physics, then the mathematical physics pathway can be good. And then quantum science and information. You might say, did I just hear that in engineering physics? So in engineering physics, it was quantum science and engineering. So maybe a little more emphasis on the hardware and how you might build quantum computing systems. And here, quantum science and information, a little bit more on what is the fundamental nature of information at the quantum level. So, because the information is not carried in bits, that could be a 0 or a 1, but instead you might have heard of qubits, so a quantum bit that has a certain probability of being a 0 and a 1. And Mark mentioned entangled states. Okay, so entanglement and kind of information there. These are the kinds of things one might study in quantum science and engineering and information. But there'd be high overlap with quantum science and engineering. You know, a lot of physicists do experimental physics and will also be working on applications that are relevant for quantum computing. And then finally, physics education. And so how can we improve student learning of physics concepts through improved pedagogical techniques? And you might say, well, why isn't that just in the School of Education? Okay, why is this in physics? Well, in physics, we actually do experiments on this. Okay, the experiments are classrooms. And physics education research exists as a field since about the mid-1980s. And so at Stanford, we've got some world-renowned people in physics education research like Carl Wyman. And so there's a pathway for that as well. Okay, so 7 specialties, 7 pathways. They give you a sampling of the kinds of things you might study in physics or engineering physics. We started a little bit late, but I'm going to go really quickly through the rest. How can you engage with the physics and engineering physics student community? So you could take physics courses, almost all of which are taught with engaged learning techniques. I had even online, because even when we were teaching remotely, we were doing things very engaged. You can join one of the physics-oriented societies, and basically physics and engineering physics students just kind of blur together in all these things. So there's a physics society, there's a Stanford Astronomical Society that's very active, an engineering physics interdisciplinary community that's a little bit in a lull right now, and then the Physics Undergraduate Women and Gender Minorities at Stanford, or PUMAs, tends to be a very active group as well. So you can look for those online. Are there some sampler courses? Yeah, there are some freshman seminars. Actually, when I was putting this together and updating it for this year, I realized that we offered almost everything in the fall. And so this is a little bit late, unless you're already taking one of these. In the future, I think we should try to spread out our freshman seminars a little bit more into the winter and spring as well. But the freshman seminars can be a good way to be introduced to some of these. So there's one in the winter called Physics in the 21st Century, Physics 83N, that you might apply for. If you're interested, what do physics and engineering physics students do after they graduate? All kinds of stuff. A lot of students will go on for higher education, so either a master's degree or a PhD. In physics, it's probably about 60% of our students go on and get a PhD in physics. In engineering physics, it might be 40 to 50%. Okay? But not always in physics. Like physics will go over into engineering. Engineering physics will go physics or engineering. Then a number of students will go into the industry or the private sector. So examples are data science, engineering, startup founders. Last time we looked at the data, among our physics majors, like I think we're looking at about 120 recent physics majors, I think none had started a company. Of the engineering physics majors, I think out of 30 or so, 3 had started companies. Okay, so there definitely is kind of like a choice going on there. Then in the upper right, a way of thinking. So public service, policy, analysts, think tanks, consulting firms, they often love physics or engineering physics majors because you're kind of trained to think about any problem, like not just in a particular domain. Also, teaching. Okay, we had the physics education there. Even our graduate students, sometimes working on their PhD, they realize that what they love most about it is serving as teaching assistants for you, okay, the undergraduates, and then go on to do teaching. Or professional degrees like medicine or law. Actually, physics and engineering physics students do really well on the MCAT and LSAT, okay, the standardized test for medicine and law. They're self-selected. They're ones who are interested in medicine and law. But it is a good background for that. Also, we have majors who end up in the arts. And I write writer, dancer, artist, because I can think of students who did exactly that. Okay, so this is not just in the abstract. They have fun doing physics and then go off and do the arts. So how can when and how could you get involved in research? Being involved in research is a really big part of being a physics or engineering physics undergraduate. And I would say as soon as you are interested, we welcome freshmen to apply. And you might say, well, how do I apply? So if you want to work with faculty in the applied physics, SLAC, or engineering, then apply to the Physics Summer Research Program. And when you get the slides, that link will take you to our site. You'll receive a stipend of $5,000 plus travel and living adjustment up to $2,500 and a needs-based adjustment as well on top of that. And we hold an informational lunch typically in late November. In physics, if you're in Physics 41 or Physics 61, we'll announce there. And maybe I could tell you when we're having that informational lunch. Because at it, we will then tell you about how to get involved in this program. Some opportunities are geared towards first-year students. Okay, we ask faculty, do you have any projects relevant for first-year students? And more than half the faculty check off yes, okay, that they do. And we help match students to faculty. We have a spreadsheet you can look at of our 2022 positions to see examples of what students do. How do you get started? The first 5 courses in physics, these 5, are required of all physics and engineering physics students. So this is different from other areas of engineering. We require physics 41 and 43 or equivalent. Some students will place out of 41 or 41 and 43. Okay, so you can start at the right point in the ladder. Some students are ready to start in physics 61. All physics and engineering physics students are required to take 61, 71, and 81. That's new this year, but you're all first-year students, so it's not new for you. It is the way it is. And so then everyone is really well prepared at the same level. You take the placement diagnostic in the fall to find out where you place in the sequence. And we have sample plans that you can click on later that show you the first 1 or 2 years of how to get started. We have 6 different plans, okay? So that's like, never feel that it's too late for you to start. But if you are interested and aren't yet taking physics 41 or haven't placed out of it, then definitely take physics 41 in the winter and then 43 in the spring so that you can do 61, 71, 81 next year. Math 50 series is recommended for physics majors, required for physics majors, recommended for the others. And I am just going to leave this information for when you get your slides. It's how to contact people for pre-major advising, including me and Mark. And yeah, and I think we've already gone over the specialties and the pathways. Join a student group and look out for these announcements about group advising sessions. Okay, so these last slides are more for your use later when you get the slides. Okay, thank you.